A robotic arm hovers, solder paste glistens. In seconds, a microchip snaps into place. This isn't science fiction. Without these palm-sized computers, your phone wouldn't boot, your car wouldn't start, and planes wouldn't be able to land. Before a single wire is soldered, the process begins in silence on a screen. Engineers feed performance requirements into advanced simulation software, processing power, heat tolerance, memory allocation, port placement, the whole shebangs. Every trace of copper, every microsecond of data flow has to be mapped with mathematical precision. The result is a schematic, a two-dimensional maze of pathways, barely wider than a human hair. Once the logic is sound, the layout becomes a blueprint, a multi-layered design that compresses what once filled a shoebox into a board smaller than a credit card. Some mini PCBs carry over 1,200 components in under 10 square centimeters. Resistors, microcontrollers, even wireless modules, all packed tighter than city blocks. Well, now that the blueprint is flawless, the real work begins on the factory floor, starting with the board itself. It all starts with a flat sheet fiberglass core, clad in copper. Machines etch away microscopic pathways, carving the blueprint into physical form. Each layer is aligned using optical targets, then bonded with resin under pressure and heat. Now, this is the spine of the tiny computer, a multi-layered, printed circuit board capable of routing signals faster than the blink of an eye. Vias, or tiny holes, are drilled using lasers or diamond-tipped bits, allowing signals to pass between layers. Copper is deposited through these holes, creating vertical highways in a horizontal city of circuits. Every board is then coated with a green solder mask, revealing only what needs to connect. It looks finished, but it's just a skeleton. But the thing is, a circuit board without components is just potential, waiting to come alive, like Frankenstein's monster. Factories don't build everything from scratch. Instead, they wait for shipments, microchips from Taiwan, capacitors from Malaysia, power regulators from South Korea or Tashi Station. Each component arrives sealed, sorted, and labeled to match the blueprint's exact coordinates. Every resistor is measured in ohms, every capacitor in farads, and every tolerance is precise. A mini computer might need over 500 individual parts, many smaller than a grain of sand. Over 60% of SMT components come from just 3 manufacturing hubs in East Asia, where global supply chains are timed to the hour. Inside the factory, workers or automated feeders sort these parts into reels and trays, ready for the machines. This step is called kitting, a digital assembly line preparing for a symphony of precision. With all parts in hand, now the robots take over. Okay, this is where speed meets precision, where machines begin to build with sight. Pick and place machines don't look like they work very fast until they start moving. In a blur, mechanical arms draw tiny components from reels and trays, swinging into position at hundreds of placements per second. Each piece is aligned with laser-guided accuracy, landing on its spot with sub-millimeter precision. What makes it possible? Vision-guided heads. Cameras track each component in real time, adjusting for angle, rotation, and even humidity-driven expansion. This is so much more than movement alone. It's correction in motion. The board glides along a conveyor under a dozen heads working in perfect rhythm. Resistors, capacitors, microcontrollers, they all find their place on pads coated with microscopic dots of solder paste. Thousands of placements, 0 human hands, and absolutely no room for error. But all of this precise placement means nothing until heat seals every connection into something permanent. Okay, so next, these components are fused to the board. The freshly assembled board now moves into one of the most critical stages, reflow soldering. It enters a long, tunnel-like oven, divided into multiple thermal zones. As it glides forward, each zone gradually increases the heat, carefully designed to prevent warping or thermal shock. At precisely 464 degrees Fahrenheit, the solder paste melts. Microscopic metal particles liquefy, bonding components to the copper pads. This might seem like glue, but it's electrical lifeblood. Each solder joint must be strong, conductive, and durable enough to survive years of heating, cooling, and movement. Then, just as precisely, the oven cools. The solder hardens, locking every component in place. From start to finish, the process takes under 7 minutes, but one misstep and the entire board fails. And that's because even the tiniest invisible flaw can kill the entire machine. But how do we know that every connection survived the heat? Okay, so the board is complete, but it's still a little iffy when it comes to the trust department. So now it's got to go through a gauntlet of automated inspections. First up is the automated optical inspection, where high-resolution cameras scan the board for defects in solder, alignment, and missing components. This is crazy because it takes less than 1 second per board. Next up comes X-rays. This is especially useful for hidden joints under processors and multi-layered connections. X-rays reveal internal structures no camera can see. Finally, flying probe testers descend. They touch down like insect legs, sending signals through dozens of nodes. If even one circuit is open, one micro break, and a trace, it's caught. That board is flagged, logged, and either reworked or rejected. In high-volume production, these steps prevent entire shipments from failing in the field. Now, with a clean bill of health, our tiny computer is almost ready to live outside the board. But here's the thing, a board is only as good as the body that it's housed in. Now, that's because no matter how powerful the board is by itself, it's also fragile. So our next step is dedicated to give it protection, structure, and usability. Plastic or aluminum enclosures shaped by injection molding snap perfectly around the board. Every dimension is exact down to the millimeter. Fraction of a millimeter off and the port won't align. Molds for these cases can cost over $50,000 each, and that's just a prototype. But once perfected, they deliver thousands of shells with flawless repeatability. CNC machines cut precise openings for HDMI, Ethernet, power, and USB. Thermal pads, airflow channels, and vibration mounts are also added for protection. This isn't just packaging, it's engineering for durability, and each unit is sealed, then checked again for port alignment and mechanical fit. And now the brain has got its armor. So now it rests, silent, sealed, and breathless, waiting to be brought to life. Once the hardware is sealed, it's time to do just that. Engineers connect each unit to a programming interface where firmware is flashed onto onboard memory. This includes the bootloader, what the computer sees first, and BIOS or UFED, depending on your board, which manages the hardware. And next up comes the operating system. Over 90% of many computer manufacturers pre-install Linux-based distributions, stripped down for efficiency and speed. These systems are tailored to the board's exact chipsets and thermal limits. Drivers are installed to ensure audio, video, wireless, and USB ports function instantly out of the box. Some units even receive custom software packages preloaded for industrial or educational use. The final step, a full system boot, right there on the production line. Our tiny computer can now boot, but a question remains, does it pass final quality checks? And that's because no machine can be completely trusted until it survives fire and time itself. With its mind awakened, the computer now faces one final trial, burn-in. Each unit is slotted into a stress testing rack where it runs continuously under load, maximum CPU usage, active memory, video output, and networking all at once. The goal? Force potential failures to surface before they reach your hands. This process can last up to 48 hours. It's long, hot, and unforgiving, but it works, catching 99.8% of early life hardware defects. Systems that overheat, freeze, or crash are flagged, disassembled, and diagnosed. Those that endure, they earn their serial number. After passing, each unit is cleaned, labeled, and boxed. Anti-static bags protect the board, shock-absorbing foam guards the casing, and just like that, it's ready for the world. From here, it ships to you and right into the heart of your next project. What began as an idea on a screen is now a fully functioning computer no larger than your palm.